Okay, so let's get back into it. Okay, so one tricky thing about regressions is that we can only have variables that aren't totally correlated with one another on the right-hand side. So here, imagine that we have this fellow or this lady, and we have his or her wages over time every year, and we want to see how that's related both to his or her age and what year it is. So that you might think, oh, like we'd like to be able to control for the year because there are differences in the economy each year, and we'd like to be able to control for those. So the problem with that is that the age and year are perfectly correlated. You gain a year of age every year that passes in the data, and it makes regression analysis impossible. You can't figure out, the regression cannot figure out which part of the wage changes is from age and which part of the wage changes is from year, because age and year are perfectly correlated. Every time you have a 1 year increase in the age, you have an identical 1-year increase in year. So we call this multi-collinearity, and it makes regression analysis totally impossible. So that's just, if for instance, the case where this might come in is, say you did a regression and you're regressing wages on beta naught plus beta 1 male plus beta 2 female plus U. So beta, so what's interesting about this is, in the data set, this is going to be a column of ones. Male is going to be a column of zeros and ones, and female is going to be a reciprocal column of zeros and ones. So where male is 1, female will be 0, or where male is 0, female will be 1. And what that means is that these three together are collinear. You can add, for instance, if I added these two columns on the right-hand side, it would produce the column on the left-hand side. If you can do that, the regression simply can't run. It can't figure out what's because of male, what's because of female, because those together are collinear with the intercept. So we call that multi-collinearity problem. The teacher that taught me said he called it a dummy variables problem. And he said, if you did it, it meant you shouldn't be an economist, or something. He had some kind of funny thing to say about if you tried to do this, it meant you needed to get another major, you needed to change your major. Okay. Questions about that? Another good example is, say we put into the regression your height in inches and your height in centimeters. So these are really just two ways of measuring the exact same thing. The regression can't figure out which is the thing, what's the effect of the height in inches and what's the effect of the height in centimeters, because they're totally the same. They never differ. So the regression can't figure out which it should be, it can't figure out the effect of them both. Okay, yeah, questions on that? That's worth thinking through. Warren, Stephanie, Noah, Ned, Leanna, Kimberly. No questions, okay. Okay, so omitted variables bias. This is maybe the center of the class. In my opinion, this is the center of the class. Omitted variables bias. And omitted variables bias occurs when there's an important causal factor of the outcome you're interested in, but it's not included in the regression. And what it does is it results in the effect that you're interested in either being overestimated or underestimated. Like a classic kind of example is, say we're interested in the effect of education on wages, but there's a powerful causal factor called, I don't know, IQ or like work hard culture, work hard. And each of these has an influence on wages as well as on education. I wish I wrote this one in a different color. So like work hard culture. Do you know anyone that they couldn't go on, they worked really hard. They were from a family that was really high achieving. So it might be that work hard culture both increases someone's education and it increases how much they would earn in the labor market, even if they were prevented from getting education. In the same way, IQ might make education easier for someone. So it's easier to go through lots of years of education if school is not very challenging for you. And even if you were prevented from getting education as a high IQ person, maybe you would have greater wages or something like that. These are just examples. So this problem arises if the omitted variable, so these are two really important conditions. An omitted variable problem arises if the omitted variable is correlated with the outcome that you're interested in, and it is also correlated with the other factor that you're interested in. So we were interested in education affecting wages. This third factor that we're interested in, for instance, has to be related to education and also to wages. If it's not related to education, but it's affecting wages, that's fine. If it is correlated with education, but it doesn't affect wages, or it's not correlated with wages, that's fine. And obviously it's fine if neither path is, if it neither is correlated with education nor wages. The only thing it can't be is correlated with both education and wages. So when that happens, we have trouble right here in River City. I don't know if you guys have seen The Music Man, but it's very good. Okay. So imagine that we have a true equation. Our true equation is here, which when I say true equation, what I mean is that y is in actuality a function of x1 and x2, or rather that x2 needs to be controlled for to estimate the beta 1. And so this often happens actually in econometrics, is that what we want to estimate is some big regression like this blue one that I've marked up in blue. But because of data limitations, we're missing x2 in the data. And that's true in all sorts of things. Like, it's just hard to measure people's motivation. It's just hard to measure people's culture. It's just hard to measure people's IQ. You can't, if you have a big data set from the census, you have a lot of information about them, but you're missing stuff that might be important. Okay, so this is the data. This is the data we wanted. This is the data we have. It's like that Batman quote, you know, like the hero we have and not the hero we need, or something like that. So we've got the hero that we have and not the hero that we need. And suppose the x2 and x1 are correlated. So we can write this. We're going to write a function of how x1 and x2 are correlated. x2, if we regress it onto x1, would give us a regression equation, delta naught plus delta 1 times x1 plus an error term, which we will call eta. Eta. We're learning all sorts of Latin. Delta, and eta. Okay, so we can write x2 in terms of x1 because they're correlated. So this is pretty cool. It looks like, okay. So remember that we're only able to estimate this regression here because we don't have x2. What we know is in the background there is an x2 lurking, and everything that's not in the regression is in the error term. Okay, so we can rewrite the error term in terms of a part that's explained by beta, by x2, and a residual that's not explained by x2. So that's where this is coming from here. Okay. So we can also, we have one more substitution, which is that, remember, x2 can be written as a function of x1. We have delta naught plus delta 1 times x1 plus eta. And so we're going to substitute in for x2 this expression of x1, because that's what's the x1 is what's actually in the data. Okay, so what can we do? Now we can, we're going to multiply through this beta 2. And that's all this is right here, is we multiply through beta 2. And then what that allows us to do is to gather terms. So we're going to put together everything that doesn't have an x in it. That's beta naught and beta 2, delta 2. So we're going to put those together. These are, you notice, the constant terms that are there. So they're not part of the x. They're part of x1 or x2. They're just part of nothing. They're just constants. We can put together also, let me see if I can find another color really quick. How do I get out of here? So those that have coefficients on x1, we can bring together as well. And we can factorize out the x. So that's why we have x times beta 1 plus beta 2 times delta 1. Okay. And then we're going to also finally bring together the parts that are have error terms in it. So we have eta and we have epsilon that are everything that's connected to eta and epsilon will be the new error term. Okay, so what do we learn? We learn that the beta naught that we're able to estimate is slightly wrong. The beta naught that we're going to estimate is the true beta naught plus the beta 2 that we would have estimated times the delta naught, which is the intercept from x2 on x1. We learn that, sorry, my stylus. We learned that the beta 1 that we're able to estimate in the data is not actually the true beta, because notice that the true beta would just be beta 1. Instead, we have that the beta that we're able to estimate is the true beta 1 plus beta 2, which is the true effect of x2 on the outcome, times delta 1, which is how x2 changes in response to x1. Okay, and then the error term isn't the original error term either, but that's not such a big deal. The main deal that we'll be thinking about is this beta 1 formula, which I've written simply right here. So this is definitely worth memorizing. I feel like when you memorize something, it becomes a part of you and you can understand things better. So this is definitely worth memorizing. Of course, you'll be able to look it up during your exam, but I really think that there's some deep learning that happens when you commit something to your memory. It becomes a piece of you. And basically, all we learn from this is a very important but simple truth, which is that the beta 1 that we're able to estimate, if we don't have data on x2, is the true beta 1 plus basically the relationship between x2 and y times the relationship between x1 and x2. So this right here is called the bias term. This is how far off is the beta 1 that we can estimate from the beta 1 that we actually wanted. And so the bigger the beta 2, the bigger the delta 1, the larger the bias. It also it reinforces something that we've said earlier, I'm going to delete some of this math because it's just a big mess. It also reiterates something that we've said before, which is consider the case in which beta 2 is 0. If there is no effect of x2 on the outcome, then there's no bias because the new beta that we're able to estimate is equal to the beta we wanted plus 0 times delta 1, which is just beta 1. Okay. Similarly, if delta 1 is equal to 0, which is to say, if x1 and x2 are uncorrelated, the beta 1 that we're able to estimate is the true beta 1 plus beta 2 times 0, which is just beta 1. So if either there is no relationship between x1 and x2, or x2 has no effect on the outcome variable, then we get the beta that we estimate without x2 is the true beta. Okay, let me stop and answer questions there. Denelson, Cameron, Derek, Devin, Esmeralda, Katrina, any questions?
I have a question.
Yeah.
So you said when it's equal to 0, that's when the B star 1 is equal to B1, right? That's the only condition, right?
Yep. So if either beta 2 is 0 or delta 1 is 0, then the beta you estimate is the true beta.
Okay. For sure. Thank you.
Yeah, my pleasure. That's a great question. And I'm just going to say this this bit in maybe slightly different words, just to make sure that this is clear. The beta star is the beta you estimate if you don't control for x2. The beta 1 is the true effect of x1 on the outcome. Okay? Okay. No other questions? Okay. So that's a really important piece. This is really interesting too. So the bias term is beta 2 delta 1. What that means is that the bias, we can calculate what size the bias is if we know something about the relationship between x1 and x2 and the beta 2 itself. So for instance, what if x2 has a positive effect on y, so that is to say beta 2 is greater than 0, and x1 is positively related to x2, which is to say delta 1 is positive. If that's the case, is the bias positive or negative? So let me do it with you guys. So we know that beta 2 will be a positive number because x2 has a positive effect on y, beta, which is the same as saying beta 2 is positive. And delta 1 has a positive, will have a positive, is a positive number as well if x1 and x2 are positively related. So what that means is that the bias is a positive number times a positive number, which is a positive number. So what that means is that, say we have a beta, the effect of education is 0.08, and we have a positive beta 2 and a positive delta 1, we're going to tend to estimate a beta 1 that is larger than the true beta 1. So it might be 0.12 instead. Okay. So it's a beta, the beta that we're able to estimate is going to be larger than the beta 1 that's true. So let me do a small example. Instead of beta 2 being positive, what if beta 2 is negative? So there's a negative relationship between the beta 2 and, I'm sorry, between x2 and the y. Well, what that means is that the bias will be negative in that case. So say here in our example where we know that the true effective education is 8% increases, and we know that the bias will be negative because it's a negative number times a positive number. Well, then the actual estimate that we get for the beta, if we don't control for x2, is going to be smaller than 0.8. So it might be something like 0.03. Okay, that's a negative bias. We're underestimating the true effect. That's really interesting and important. We can kind of think carefully about what kind of bias we will have in our estimates. Okay, so instead of estimating beta 1, we estimate, these are just some examples. We estimate this piece with a delta in it, a bias term, a beta times a bias term called beta 2 delta 1, where education is emitted. I'm sorry, where IQ is emitted. So beta 1 is going to tend to be biased upward, which means that the coefficient on education is too positive, because what we think is that IQ has a positive effect on wages, and education and IQ are positively related. So we're going to tend to overestimate the effect of education. I'm going a little bit faster than I would like to, just because I would like to go through a couple examples with you. So that was, let me see here. We're so out of time. Okay, let me do one more example. This is the same one. I think this is a concrete example that can help us think through it a little bit. So say that we're estimating, we still want to know the effect of education on income, and we have to omit from the equation IQ. IQ is positively correlated with your years of education and also your income. And so what we think is that the 1500 that we get as a coefficient on education is positively biased, which means it's larger than it should be because we've omitted IQ. And then say that we're able to go out and collect IQ for everyone that was in our data and re-estimate this equation. And so what we'd find is that, possibly, is that instead of $1,500 coefficient on education, we would get something smaller, like 800. And we learned that IQ would have a strong positive relationship with income. So these last slides through 27 are really great examples. Like, these are just great work examples. We can come back and do these examples together tomorrow if we finish the 8th deck. We got to finish the 8th deck tomorrow, and but I think we can do that, and then we can either come back to if this isn't super clear, we can come back and do these, or we can do some homework questions together that would kind of get us ready for the exam. But whatever we think is the best way towards the exam. I'm guessing. Could I just take a little poll? How do I do a new poll? Okay, do you want to have more practice with omitted variables bias or do practice homework problems together. And we could make the homework I can either, if you guys want, oh, where did it go? So they'd be new homework questions, but we would, how do I launch it? Entitled poll. How do I do it? I don't understand. That one was so easy. Oh, did it come through?
I don't see any phone.
Okay. Okay, let's see if that works. So I'm happy to do either. The omitted variables thing is just such a core piece of that class that I it'll be part of the test, of course, but also it's a really important kind of feature. And we could do omitted variables questions in homework. So maybe they're not mutually exclusive. Okay, sounds good. That's pretty decisive. Sounds good. So what we'll do is tomorrow, if we have extra time, I'll have a homework ready that we can do together. And on Thursday, we'll do a little review session and maybe we'll do some more homework or something like that if we have time. Okay, sounds great. I will hang back and take questions for a minute, but feel free to leave if you would like. My pleasure. Thanks, Derek. Thanks, Stephanie. Thanks, Leanna. Thanks, Noah.
Catch you later, Professor.
See you back.
Question. Have you noticed the recent conflict in Nagorno-Karabakh again? I mean, in Armenia?
No. What's happening?
So this time there's conflict on the Nakhchiv side of the border. So it's on the southern side of the border rather than the northeast. So it's just like another world conflict.
Oh no, that's not good.
Yeah, that's really it. Questions or opinions on the space launches?
No, I don't have many opinions. Let me think. The space launches. What happened with the space launches?
Recently, there was the Virgin Mobile like launched, and then there's the Jeff Bezos launch. Like who has their biggest space penis in space?
Well, I have to say I am a big fan of space exploration. I think people need frontiers. I think they need things that are unexplored, and they need to invade them and learn them and expand from them. Whether it's, I mean, lots of things are just efficient in certain shapes. So I don't really fault the engineers for for shaping aerodynamic
like phallic symbols
vehicles as narrow and long. That's just sort of what flies most easily through friction. It's not really an expression of male anything, but I know it's very popular to say everything is a penis, but physics is also a real thing. And if you made a big umbrella spaceship, it wouldn't get very far.
It wouldn't. Yeah. There's engineering behind it too. I agree.
Say again.
And there's engineering behind it. I agree as well. It's just it's just nature.
Yeah.
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 All right.
Okay. Are you doing good?
Yeah, I'm doing all right. I'm just when I have trouble, I just look over the slides again, and it's pretty kind of easy to follow through.
Oh, good. I'm glad to hear that. I think that's true.
You know,
Say again.
it's very patterny, and like recently, this last slide that you did really helped like to visualize it a lot easier, than other times, because you're actually seeing how things are literally just tied one to another.
Yeah, and sometimes it's just hard to see it on the first time through. So so I've done a ton of work to try to make the slides as clear as possible.
Very
So if you think that's working, then that's great. I'm very, very glad to hear that.
Yeah, I just wanted to let you know that I like how you make us understand the pattern, which it feels crucial. Because I took 105 earlier this summer, finance, and it's like it's very similar, but also it's like it's the same thing. It's in the end we ended up using you need the calculator to do everything in that class. But it's also like it was kind of hard to understand that because sometimes when the teachers explain the concepts, you see a bunch of redundancy and like patterns,
Yeah, for sure.
It's like it's not as complex in this class. In this one, it's simpler.
Oh, good. Well, I'm very glad to hear that. That's great.
It's more straightforward, In the other class, it's easier, but it's so redundant. It's long.
It's easier, but redundant. Yeah, gotcha.
This one, it's more complex, but it's straightforward, so it's easier.
Oh, good. That's great. That's exactly what I would hope for this class. That's wonderful.
Yeah, that's all I felt I should say, Professor. Oh, thank you very much, and have a good lunch.
Okay, bud. Thanks. Talk to you soon. I'll see you tomorrow.
See you.